Hi, today we're going to talk about the law of sines. Now, what is the law of sines, first and foremost? Well, it's a trigonometric relationship that we can use to solve a variety of problems that we wouldn't normally be able to solve. And at this point you might say, well, that's not true. I mean, I know trigonometry, right? I know my sines, my cosines, my tangents, and I know when to use them, right? Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. Well, that's all true, but that's only when you're dealing with right triangles. What about when you're dealing with triangles that don't have a right angle? Those rules don't apply. What about when you're in situations where you don't know all the angles and all the sides of a triangle, and it's not a right triangle, so you can't use your trigonometric functions to find the answer? Well, that's where the law of sines comes in. And today we're going to be going over what the law of sines is, how to use it, and why it's worth knowing. So, we have a triangle right here. We can tell off the bat that it's not a right triangle. There's no markings, there's no little right triangle marker. We don't have any of that, right? This is not a right triangle, which means we can't use our trigonometric functions. Well, not quite, at least, right? What I can do is divide this triangle into two other triangles using an altitude and create two right angles here and here. So I've split my triangle into two right triangles. That means that we can use our trigonometric functions, right? So ka, toa is what we use to remember them, right? And let's say, oh, well, the sine of angle B is going to be this opposite side here over the hypotenuse, which is A. I'm going to call this opposite side x just to make things easier for me, right? So x over A. I could rewrite this as A times the sine of B is equal to x. I just multiply both sides by A, right? And I can do the same thing on the other triangle, right? I can say the sine of A is equal to x over B, or B times the sine of A is equal to x. And here we notice something, right? These and this, right? They're equal, right? They're both equal to x, which means that A times the sine of B has to be equal to B times the sine of A. Because, well, they're both equal to x, so they must be equal to each other. And I'm going to divide both sides by AB. And you'll see why I did this, because A's cancel out here, the B's cancel out here, and I'm left with sine of B over B is equal to the sine of A over A. And besides being a, cute little relationship, oh, look, B and B, A and A, it's a secret. It's a magical, mystical relationship that allows us to unlock every part of the triangle, because we can expand this to include, if this angle here is C and this side length here is C, we also have sine of C over C is equal to all this. And that's when we get absolutely crazy. This is the law of sines, which allows us to relate every angle in the triangle with every side length in the triangle, which in turn allows us to solve for anything on this triangle, just given a couple angles or a couple side lengths. To go over how to do this, let's go over a couple example problems where we'll use actual numbers and not variables to see just how the law of sines is so completely overpowered. Right? So as an example, let's say we're solving for a side length, right? And I have a triangle here, which of course, I'm not drawing to scale because it's hard, but with a 30-degree angle and a 45 degree angle. And I know that this side length is 2, and I want to find out what this side length B is, right? Now, I see two angles. I see that I have to solve a side length that I can't normally get. I see that this is not a right triangle. I'm thinking the law of sines. But how exactly do I know, for example, which angle goes with which side length. The key is always, always, always opposites, right? I have an angle here, right? That corresponds with, at least when it comes to the law of sines, this opposite side length here. I have an angle here, right? This corresponds with the opposite side length here. So if I were to write this out like the law of sines, I would say sine of 30 over 2, it's my matching side length because it's the opposite, is equal to the sine of 45 over b. And we're not going to worry about this angle and this side length because we don't need to know that information to solve the problem. We only have to focus on these two. And it doesn't really matter, for example, which one is A or B or C. The individual variable names don't really matter. All that matters is that you're using the corresponding angles and side lengths, which are always going to be opposite from each other. So let's actually go ahead and solve this problem. All right, the sine of 30, that's a common trigonometric function value. It's a special right triangle. So 30, 60, 90 right triangle. Just a quick refresh. We have a 30-degree angle here. This is a side length A. This is a side length A root 3. This is a side length 2A. Sine of 30 then is A over 2A, or by default, 1/2. Right? So we have 1/2 over 2, which is just 1/4, is equal to the sine of 45 over b. We want to find b, so I'm going to multiply both sides by b. And I have b over 4 is equal to sine of 45. I'm going to actually multiply by 4 as well, so I can get b all by itself. So b equals 4 times the sine of 45. Sine of 45 itself is actually another special right triangle. It's a 45-45 right triangle. So we have a 45 degree here, right triangle here, 45 degree. I have A root 2. So the sine of that is just root 2 over 2. Right, so 4 times root 2 over 2 is equal to b, which is equal to 2 root 2. And just like that, I find a side length that I would not have been able to find otherwise, just using the law of sines. Now, let's say we wanted to find an angle, because in this case, finding the angle here, right, this angle C would be pretty trivial, right? We know the sum of the angles in a triangle adds up to 180, right? So this side length C would just be 180 minus the angles we know about, right? We know about 45, and we know about 30, right? So C would just be 180 minus 45 minus 30. Well, the law of sines comes in very, very handy when we don't know all of our angles, when you can't use that angle trick, right? We just know one angle, right? Let's imagine that I'm standing here, and you're standing here. And I, for some reason, will make it a little more detailed. For some reason, I'm sending up a drone, right? That's here, right? I'll just call this X, right? And it has an angle down towards you, like this. I'm tilting it up. I'm going to plunge it down towards you. Now, what is this angle theta? I know I'm launching it, right, at a degree of 40 degrees, and then the distance between me and you is 40 meters. And I have a sensor on my drone that says, hey, from you to the drone, that's a 30-meter length. But what's that angle, right? Now, finding this angle, if we knew this angle, right, if this was, say, 75, this would be incredibly easy. I'd just do 180 minus 40 minus 75, and I'd have my theta right here. I'd have my answer, but I don't have this. I don't know what this is, which means I can't use my 180 trick, right? I need at least 2 angle measurements for that, and I only have 1. What I do have, though, and this makes me kind of happy to see, I have an angle and an opposite side length. Angle, opposite side length means I can write this as a law of sines. I can say sine of 40 over 30. which is actually equal to this sine of theta, right, all over the opposite side length, which is 40, right? And I want to find theta, so I'm going to multiply both sides by 40 just to get theta all by itself. I have 4/3 sine of 40 equals the sine of theta. I'm actually going to take the inverse sine of both sides, so I can just get my theta, right? So the inverse sine of 4/3 sine of 40 equals theta. Now for this, I'm going to need a calculator because these values are, I don't know off the top of my head. But I get a calculator, I plug that in, I find theta is equal to 58.99 degrees. Right? And just like that, I've solved my problem. I know my drone's tilted 58.99 degrees. It's plunging towards you. How happy does that make you feel? Well, not particularly happy, but that's not the point. The point is that we used the law of sines to find an angle when the situation looked kind of bleak. Right? We didn't have much information. We had all of 2 side lengths and a single angle. But we were able to find the angle we needed using just that information. And that's why the law of sines is so great. So, 2 tips. First, always look at a problem and see if there are opposite angles and side lengths. If there are, you can use the law of sines. If there aren't, well, try a different strategy. Second, when using the law of sines, you don't need to write it out for all 3 side lengths and angles. As you can see, we never really used this angle here and this side length here. Those didn't matter for us, so I didn't write it because it'd just be something I wouldn't use and I'd have to deal with anyway. I only used these 2, so I only wrote these 2. And finally, I'll add a third tip that goes for every single math problem. Relax, focus on what you want to find and what you know. You do that, and you will solve every problem you come across. So, that's the law of sines. I hope you found it helpful, and I hope you have a great day.